Recording in progress.
So it's time to start our last session, and the first speaker in the session is going to be our chairman for the session, Jose Crespa from Max Planck Institute for Nuclear Physics, Heidelberg. Please, Jose.
Okay, thank you very much, Olga, for the invitation, and thank you very much for joining on the 4th of July from the various places. So I will present our present work on highly charged ions, and certainly during this meeting, you had the opportunity to listen to various talks explaining how bound electrons can be used as sensors for everything, all the now interactions. So electromagnetic interaction, electroweak interaction. These are the primary interactions of the electron, but indirectly through the hyperfine interactions, the electronic wave function is also sensitive to the nuclear magnetic moment and distribution of the nuclear magnetic moment, the nuclear charge distribution. It is sensitive to the nuclear mass, to the nuclear binding energy. And one can simply also say that the ground state wave function of an electron has infinite time to adapt to any properties of the nucleus, and no matter how small. The question is how do we become able to distinguish these different interactions, and that will require controllable parameters. So we have seen in recent time very beautiful examples how clock monitoring and comparisons can test and exclude dark matter candidates, and how the time variation of fundamental constants, in particular of the fine structure constant alpha, can be studied by means of clocks. How many of these sensitivities arise from the hyperfine couplings. There are also beautiful recent works on the studies of the Lorentz violation, whereby trapped ions are studied in different orientations in the magnetic field, while the Earth moves in the reference frame. In general, and from very, very long time, we always had a problem when we try to study quantum electrodynamics in bound electronic systems, which is that there is a nucleus, and the nucleus is not so well known, and it perturbs the electronic structure, as we know. And so, in general, all these nuclear moments and their distributions, quadrupole, octupoles, hexadecapoles, whatever, they will affect our investigations of quantum electrodynamics of the bound electrons. And there are indeed several methods which have been devised to figure out how to squeeze the information about the QED out of the measurements. And one of the methods is the specific difference methods devised, for instance, by Vladimir Shabaev, but also the King plots, as we will see later. I will repeat that hyperfine effects are very strongly magnified in highly charged ions, and these strongly magnified hyperfine effects are really good in the sense that they will make the measurements, the quantities we're interested in observing in the laboratory, much larger. And at the same time, the effect of the nuclei will be also magnified. So we also know that the transition frequencies are modified by the reduced mass effect. The nucleus is not infinitely heavy. The nuclear size effect, generating a field shift due to the extension of the nuclear potential. And this also applies to the nuclear magnetization distribution. In addition, one can imagine that there are spurions. This is a term which was coined by Julian Berengut, that will be nonlinearities which mimic new physics, and we have to be able to distinguish them. And for that, the generalized king plot method has been recently presented. And this generalized king plot method needs, for a given number of unknown contributions, a large number of isotope pairs and transitions such that the information can be extracted. So I will not discuss the king plot method. It is well known, but in general, we parameterize all these small perturbations of the electronic transition in first order regarding the nuclear size distribution, the field shift, and the mass shift, and by changing the pairs of isotopes and by changing the electronic transitions of interest, one can probe the different parts of this perturbation expansion. And if you have enough quantities to play with and enough isotopic pairs to play with, you can extract the relevant information. I include here some recent references on the king plot method application for fundamental physics searches and its generalization. So now, why do highly charged ions come into play here? Well, the reason is that we expand the periodic table in the parameter charge, giving us for the same element and for the same isotope many more transitions. Not only do we gain in number of transitions, but the nuclear size effects, relativistic effects, quantum electrodynamic effects, all these interactions of the electron with the strong fields near the nucleus are magnified. So you become sensitive to new physics. Later, we will see that the highly charged ions are particularly interesting if we want to go to higher photon energies, because they are not easily photoionized due to the high binding energies. And interestingly, these highly charged ions still possess a multitude of strongly forbidden transitions in the extreme ultraviolet domain and also in the X-ray domain. So where there is a forbidden transition, then there is a clock, and one could use them. So another advantage of the highly charged ions is that the strongly bound outer electron, which we will use for our transitions, is, due to the strong Coulomb interaction with the nucleus, not very polarizable, or has this very small polarizability, which makes it insensitive to external perturbations. So we have systems which are much more sensitive to the internal physics, to the internal interactions, but can be less perturbed by external fields. And the very interesting competition and complementary method is the development of nuclear clocks, in particular in thorium-229, scandium, uranium-235. So I present here a cartoon where we see the radius in 10 to minus 17 meters to 10 to minus 9 meters. Here is the radius of the nucleus. And if we put there in this nucleus a fifth force carrying Yukawa particle showing here with a certain reach due to its mass, this Yukawa particle will overlap with the electronic wave function. And I present here two examples. The 3s electron in calcium plus, this is this curve, and we see it dives very little into the nucleus. So the relativistic electron density you've made, I call it so p squared plus q squared, and the relativistic wave function. It's 10 to minus 12 at the center, and it goes down from the edge of the nucleus quite strongly. If we do look at the 2s electron in calcium 15 plus, that will be a boron-like ion with 5 electrons. The 2s wave function has a much stronger overlap with the nucleus. And if we now multiply the hypothetical Yukawa particle wave function with the electronic wave function, we can see that this overlap is much larger for the strongly bound electrons in the highly charged ions. So even for light elements, this enhanced overlap will cause a increase in the interaction, which is very interesting. And another advantage is we can generate with the different isoelectronic sequences for every element many optical transitions, forbidden optical transitions from the ground state. Here you see examples on various ions of xenon and ions of calcium, and you can combine these forbidden transitions in King plots with forbidden transitions from neutrals or of singly charged ions, and that will allow you to expand your King plot. So we now want to go into the higher photon energies. In bound transitions in atoms will end somewhere here in the ultraviolet. If we do have a look at the bound transitions in highly charged ions, we reach well into the many kilo-electron volt domain, and that is an advantage. So we are until now only partially exploring the possibilities of frequency metrology, but in principle, we can do that with highly charged ions, and the fact that the highly charged ions are not photoionizable easily, it makes these transitions bound and narrow if the configurations match. So what frequency standards could we then look at? Forbidden transitions are well known in the community of the highly charged ions since many years. This is an example at 1450 electron volts. Soft X-rays is a xenon 26 plus a nickel-like ion. It was measured for various isotopes, and this transition, although it is in the X-ray domain, it has a lifetime of 15 milliseconds. So the Q value is in the order of 10 to the 15th. There are other examples, beryllium-like isoelectronic sequences, also for the yield very beautiful 0-to-0 transitions, which are in some cases hyperfine induced or accelerated, and they are now in the soft X-ray domain or in the extreme ultraviolet domain, as we can see here, 24 electron volts, 28, 43, and they have lifetimes in the range of seconds and Q values in the range of 10 to the 16 to 10 to the 17. So that looks good. We have forbidden transitions, which have decent Q values. Now our theoreticians at the Max Planck Institute, Junhai Liu in the group of Zoltan Harman, Christoph Keitel, they have made for us calculations, and we are aiming now at investigations in the first step of argon 6+, which has transitions with several seconds lifetimes in the triplet P2 to the ground state, and also transitions with microsecond lifetimes. So these are convenient starting points for our investigations. And as you can see here, some of them are electric dipole allowed, some of them are magnetic dipole allowed, and some of them are E2 allowed, and they provide very narrow transitions in the energy range, which can be accessed currently, as we will see with frequency comps. There are more outrageous examples. For instance, the neodymium-like isoelectronic sequence has transitions with Q values of 10 to the 28th in the wavelength range of tens of nanometers. And this is particularly interesting because this regime and the tens of nanometers can now be accessed with frequency comps. Very recently, a beautiful example measured in our institute, a group of Klaus Blum, Riemann Schussler, they were able to measure a very long-lived transition, a very long-lived metastable state of 200 electron volts with a Q value of 10 to the 25. And this transition is basically hyperfine quench. The lifetime goes down to 124 days, so from millions of years. And this tricontapole transition is so slow that it will serve as a perfect clock. One has to say also that we can handle such ions. The metastable state survives extraction, transport, and storage in penning trap for weeks. So this type of ions is just waiting to serve as a clock reference somewhere. For that type of experiment, we need intracavity high harmonic generation, as demonstrated in the groups of Yun Ye and Thomas Udem. And this intra-high harmonic generation basically produces a coherent comp in the regime we are interested. We built such a machine in my group where we produce up to 35 electron volts high harmonics these high harmonics coming out of the cavity can be now used for the excitation of the ions of interest. And this is our next task. Obviously, we have to prepare the highly charged ions. We have learned in the last years how to do it, how to produce the highly charged ions, extract them from the electron beam ion traps where they are generated, decelerate them, sympathetically cooled in a cloud of beryllium plus ions, and then in collaboration with the group of the PTB, of Pete Smith, this has led to the demonstration of the first optical clock using argon-13 plus. Another example, calcium 14 plus, will come soon. And in principle, the clock using these highly charged ions has reached already a systematic uncertainty of 10 to the minus 70. So the quantum logic scheme, which is used at the PTB for the detection of the transition, is exceedingly useful, and it can be instantly applied in combination with the frequency comb in the XUV domain with exactly the same methodology. We also have appropriate Hall traps, radio frequency traps. This is a very similar type of Hall trap as the model we built for PTB. For the investigations I have mentioned, in our case, we have built the internal part of the trap of superconducting niobium, which allows us to freeze the quantization magnetic field for 200 years and have an exceedingly low magnetic field noise and very long coherence times, even if we use magnetic sensitive hyperfine qubits in beryllium plus as the logic ion. Okay, so as I mentioned, the next thing which we have to do is we have to take the frequency comb, separate one of the harmonics containing the different teeth, and use this to excite the highly charged ions contained in the superconducting trap. We need for that test setup now with an XUV focusing system, and in principle, for not too high photon energies, we can also think of using contra-propagating beams, although in the Lambda regime that will be not useful. Okay, so let me come to an end. If we manage to add XUV transitions to the King plots methodology I have explained before, we can become much more sensitive to the presence of fifth forces, because the electrons which we are addressing with the XUV transitions, those electrons are much more deeply bound. So we can see here adding an XUV transition to a combination of optical transitions allows you to exclude one order of magnitude more in the exclusion plot for a fifth force in the nonlinearity. So this is a great advantage. And if you use optical and optical transitions, then you say exemplarily you can reach 10 to minus 14s in the coupling constants YE, YN. If you mix optical and XUV transition in your King plot, you can reach 10 to minus 15. And if you put several XUV transitions, you can reach 10 to minus 16 in this model of the mediator masses of interest. So this is particularly useful. And let me finish that in saying that highly charged ions are very good sensors like any other atoms, but with the particularity of providing magnified QED relativistic and nuclear size effects, with the particularity that they provide us many more forbidden optical transitions than if we were only using singly charged ions, and that we can find optical forbidden transitions up to very high charge states. The isotopic shifts are magnified, and since frequency metrology has been already demonstrating with high charge ions, we are pretty much hopeful in that we will be able to expand this to the XUV regime and produce beautiful experiments. So thank you very much. And I would like also to thank my students, in particular Janko, Jan-Henrik, Tobias, and Lennart, who are working in this XUV frequency comb, Julia Stang, Christian Warnecke, Elvin Dijk, and Vera Schäfer, who are working on the Paul Trapp, and the colleagues from the group of Pete Smith, PTB, in particular, Peter Micke, who was very absolutely instrumental in building this machine at our institute and continuing the experiments at PTB in collaboration with Stephen King. So thank you very much.
Thank you so much, Jose. Well, maybe I'll ask one question. Oh, Leo maybe is the first. Leo?
Well, I was just applauding. That wasn't.
Okay. Okay, I see. Sorry. So then I ask the question. So with your frequency comb, I understand that you have it up to 35 nanometer. So what particular ion you are planning to use?
Okay, so at the beginning, we are planning to use argon 6 plus. Argon 6 plus has this configuration, which is magnesium-like. Actually, it's very convenient because it has very close nearby states. So we can address first the M1 transition, which should be easy to find, and then we can try to look for the E2 transition, which is much harder to find. And it at around 14 electron volts is in a region of the XUV frequency comb where we have a decent output. Yeah, we're also working on enhancing the high harmonic yield of our frequency comb. But I think it is good to start with these 14, 15 electron volt transitions because they are very, the XUV frequency comb has simply higher yield.
So that you have enough energy in each harmonic, right? In
yes.
This case.
Enough photon flux. And the group...
if you compare the width of the harmonic with the width of the transition, how do they match?
Okay, well, that depends on the stabilization of the primary frequency comb. Now, the envelope, obviously, will be as broad as the pulse length governs, but the individual comb teeth will be ruled by the stability of the primary frequency comb teeth, which can be sub-hertz, but it will be multiplied by the harmonic order and some additional inconvenient factors. So we are not expecting at the beginning to be much better than kilohertz, but this is a good start. And for according to the theoreticians, we should be able to see something there. And obviously, by improving our primary frequency comb in the infrared and stabilizing it better, we should then be able to transfer the stability to the higher harmonics.
And you mentioned some transition like 100 of days. It's hardly possible. It seems to be built frequency comb with such stability. So what kind of application for this kind of very forbidden transition you see?
Okay, well, the usefulness of the transition, if they're exceedingly narrow, you have to apply some mechanism to broaden them. In principle, it is possible to make them a little bit broader, and hyperfine interaction does it naturally to bring you into, let's say, hours of lifetime. And what would be the use? Imagine we can have a frequency comb operating in the XUV, locked to a very high frequency at 40 electron volts. Then we are transferring back the stability at a much higher frequency also to the infrared. And so that will give, in principle, a faster average in time for the optical transitions. And the optical transitions are you can distribute this frequency stability in the optical region or in the infrared region much better. So you will have like a frequency down conversion. You are stabilizing to a very high photon energy. This you can do very fast because the frequency is much higher, obviously. And if this works, then you are actually stabilizing also the infrared primary frequency comb, and you can transfer it in the infrared domain to optical fiber.
I see. Thank you. I don't see any other questions. If somebody raised the hand, please unmute yourself if you want to ask the question. If not, we should proceed to the next talk. Thank you again, Jose.
Yes, thank you very much. And now the next speaker is Igor Pikovsky. He's a Branko Weiss Fellow and Assistant Professor at the Stockholm University, and he will talk about gravity and quantum mechanics. Please, Igor.
Yes, hello, thank you. Can you hear me?
Yes.
Yeah, okay, perfect. Yes, thank you very much. Yes, I originally wanted to talk about gravity and quantum mechanics, which is what my group mostly focuses on. But I actually decided in this meeting to talk about squeezing of dark matter axions, somewhat related, but a little bit in a different direction. And so, I think I have about 15 minutes. So I'll hope to give you kind of the main gist of this research direction. And that's based on a recent paper that we published with my student and postdoc. So let me get started. The main question we were curious about is if dark matter could have non-classical features that some of the models of dark matter predict, and that could play some role. Now, the search for dark matter in general, experimentally, it's kind of focusing usually on very model-specific confirmations. So we all know it has gravitational effects, but then specific models predict just different side effects as well. So we have searches for WIMPs, axions, and so forth, many different models. And nearly all of them stem from quantum field theory. And this is because, it's been a very successful way to describe fundamental physics, cosmology, high-energy physics, and so forth as kind of a starting point. Now, at the core, of course, there's quantum mechanics, but these quantum features of dark matter are not usually considered very much. And it's not studied too much about whether they could play a role or become visible. So this is kind of one of the core questions we're curious about. Do some of the current models allow or predict quantum features, and what would they mean? And so I want to give you an example of actually a quantum feature that does arise in quantum dark matter models. And so in particular, we focused on a specific class of models, namely so-called axion-like dark matter particles. This is a very popular class of models, especially since WIMPs hasn't been found and no other candidates. It's very well motivated, at least in a specific mass range. And in principle, these are so-called ALPs. So these are axion-like dark matter particles, which are very light masses that they have. And the mass range is pretty open. Now, the starting point of such models is usually a scalar field description. So it's how gravity couples to a scalar field, at least in the cosmological setting. And so kind of the standard story is that, you have these you have the Klein-Gordon equation for the classical field, for the scalar field. Then you have Einstein's equation that couples it to gravity. And then you place it on an expanding background spacetime. So you have, some kind of expanding spacetime where also you have this, axion-like scalar field. And then the typical approximations made are when you assume, you decompose this scalar field into two components, psi. You have also, this cosmological expansion. So this is captured just by the standard Hubble parameter with this A. And then the typical limits are that you consider weak fields, so kind of weak gravity, and non-relativistic description. And non-relativistic really because the mass here is very, very low of these axion-like dark matter particles. And what you get is the Gross-Pitayevsky type equation that describes the dynamics of this axion field. Okay, and so here I write it, with hats, but it doesn't matter if there's it's a quantum field or a scalar field, classical field. So it evolves in time with this kinetic term, the usual kinetic term, plus a self-interaction term, which stems from the fact that it has a gravitational interaction with itself. And so this is also called the Schrödinger-Poisson equation, where there's a Poissonian interaction term because of gravity of the axion field. And here we neglect this kind of homogeneous background mode that we're not interested in, and really interested kind of on the modes on top of this homogeneous background. Anyway, so this is just a standard description of kind of how these axion-like dark matter particles are described. And this has been studied, for example, in these numerical simulations by Shive and others a couple of years ago, where they compared just kind of this effective Gross-Pitayevsky model to standard cold dark matter models. And you see numerically that the features are very similar. And it's really something that kind of, shows that this is a powerful way to think about a light dark matter as well, just in this limit. And you even see some kind of wave interference patterns inside solitonic cores. Okay, so the bottom line of this is the Gross-Pitayevsky equation, and in fact, which means that this kind of field becomes a Bose-Einstein condensate effectively, describes reasonably well these low mass axion-like models. Now, is this description a classical one, or is that a quantum description? So that's kind of at the core of a question. Now, you can have a classical wave picture for that, and that is very well motivated. Namely, you can take a Hartree ansatz, meaning that there's only kind of a single mode that is relevant for your overall field. And then you have this field mode, psi, without the hats. And then you neglect any kind of additional modes and fluctuations around it. And on top of that, so that means that this field mode here evolves just classically. And then on top of that, you assume that effectively you're in a coherent state. So this kind of big quantum field is effectively in a coherent state such that you neglect these fluctuations as well of this A and A daggers that describe the single mode. And then, you can in principle build any states out of these. And so that's kind of the wave picture, and it's very useful for simulations because you basically run just classical simulations of these mode functions. However, you can have, for the same thing, whether first or second quantization, you can also have a quantum picture. And in a quantum picture, the Hartree ansatz means that you're consisting of n particles all in one and the same wave function. And this wave function is, of course, extremely delocalized. So each individual particle is, in fact, delocalized over a huge area in the universe. And that is, of course, a very kind of quantum mechanical behavior if you consider, individual particles inside this field. And there is, in fact, a debate a little bit if the quantumness is relevant in these kind of models or if it's not relevant. And so this is kind of what we focused on from a more quantum optics perspective. And let me say a couple of words why quantum optics perspective here is very useful. So the core question is there non-classicality if you assume such a model? Is there actually non-classicality produced? And the answer is yes. And I'll show that here in 2 slides. Our approach is, well, we keep the Hartree ansatz. So let's say it's only a single mode. So it's like one main kind of occupancy, but we also keep the operator nature intact. In other words, we don't assume that the system is actually in a coherent state. That's the main point. If this is the case, we can, in principle, also solve the dynamics. We just take the operator nature of the mode as well into account. And what one gets, in fact, an equation of motion for the single mode. And this equation of motion is well known in quantum optics. Namely, it's kind of this free evolution, harmonic evolution of this operator in the Heisenberg picture, as well as self-interaction terms. And these self-interaction terms stem really from this kind of Poissonian part, namely all these particles interact with each other gravitationally as well, or in this case, kind of the global mode the collective mode of the field interacts also with itself gravitationally through the gravitational interaction. And this leads these nonlinearities, and this is well known, of course, self-Kerr nonlinearities from quantum optics. And we can find these parameters specifically for the dark matter models. Here there's a kinetic energy term, this is the interaction term, and we can actually find that, in terms of the parameters of these models. So one can find this, kinetic energy effectively, and then the potential energy. And in principle, we can assume they're related by the virial theorem. So we assume dark matter particles are virialized. And so, these parameter, the main parameter here that matters is effectively just the kinetic energy of this dark matter. And this interaction parameter is also related to the kinetic energy, but suppressed by this factor n big N, which is very, very large. So large occupancy of these very light, ultralight dark matter particles. But still, there is a self-interaction term. And the question is, what does it do? And so we can plug in numbers and find out. So this mean energy we can find just from assuming how fast we're going through this dark matter background wind effectively. We can then find how strong these parameters are. Okay, and so basically the first effect that this self-granularity has is what, of course, is well known in quantum optics, namely it gives you squeezing. So the single mode, even it's not a two-mode squeezing, but it's a single mode squeezing. This is the onset of something which goes beyond the coherent state evolution, which would otherwise be given by this pure kinetic term. And the question is, how quickly does the squeezing arise, which is what we use as a signature of non-classicality in this model. This comes about because at small times and these weak nonlinearities, we can approximate it by just a squeezing operator, this kind of additional term here. Okay, and so basically what comes out is if you start with a coherent state initially, you get a squeeze state after a short time, and then there's a maximal squeezing, which is reached after a specific time, which we call Tmax. Okay, and so there's a squeezing time, which gives you a 3 dB squeezing, and you can see that it is actually very short because it scales as 1 over n, 1 over the number of these dark matter particles in the volume, which is very, very large. And the maximal squeezing, that scales with a 6th root of the number of dark matter particles. And one can compare it to other time scales, like the LPHYS' time scale, namely that tells us that the mean field approximation is not good anymore. And this is actually much, much longer. So this onset of squeezing is much sooner and much shorter than kind of your naive maybe prediction of when a kind of a mean field model would break down. And so to give some numbers here, one can look at different scenarios, like a cosmological scenario, specific solitonic cores, or along the Milky Way. So how much, basically how many dark matter particles there are in these specific volumes. What one finds is that this squeezing timescale, so generating of 3 dB squeezing, proceeds on microsecond scales. Okay, and we have to compare it to, the age of the universe. So it's exceptionally fast that squeezing is produced. And even this maximum squeezing becomes enormous. So it's like, e to the minus 36 or plus 36 of this quantum noise, which is created after squeezing time scale. Squeezing time scale could be on the matter of years. So this is, 3,500 years, for example, in a cosmological time scale. So the squeezing is produced very fast and very rapidly within these dark matter models. And that's really kind of the main take-home message. Namely, even though you maybe assume your system is actually a coherent state and you can do it classically, this is not the case. So you have a side effect of this Gross-Pitaevsky evolution, which is the self-squeezing, which proceeds extremely rapid. And so the summary of the result is you get Kerr squeezing even in the most simple models of ALP-like particles. It's created on very short time scales, microsecond scales. It's really, interestingly, this actually is independent of the mode occupation. And so, the standard hand-wavy arguments of what's classical or not don't really apply. You get enormous squeezing. And basically what it also means is that these simple models that you just say that, well, this is well described by Gross-Pitaevsky equation and it's all classical, that is kind of not well justified in some sense. And then just as a brief outlook, I hope I'm not too much over time. Of course, what we study currently is, well, do the squeezing actually decohere? And it doesn't look like it decoheres very rapidly. And so it's relatively robust, actually, because, squeezing is more robust than superposition states in general. And so, it is continuously regenerated. That's the main point. It's regenerated all the time because it's an intrinsic evolution of the dark matter particle. And so, it seems like, maybe you have to go beyond the single mode Hartree ansatz to really understand the deep physics, which also means that the Hartree ansatz maybe is not well justified for these type of considerations. And so that's kind of our next goal, to look at that more closely. Okay, and so there's two aspects to that, namely what could be the interesting experimental evidence of that, not sure, and the other one, how can one augment these theoretical models, maybe to understand better what would be a better description. Okay, and with that, let me thank you very much for your time, and these are the postdoc and students who worked on this project. Thank you.
Thank you very much, Igor, for the beautiful talk, and please, questions, raise your hand if you have a question. Or you can...
I think there's a few,
Yes.
Andy Geraci.
Andy Geraci.
Yeah, hi, Igor. Really nice talk. Very interesting. So I'm just wondering if you can say anything more about the experimental signature you would expect, say, in these haloscope searches where you look for some sort of line shape or something like that. Is there some obvious way to see the squeezing in an experimental setup?
Yeah, it's an excellent question. In fact, that's kind of really the main goal, the main motivation. I don't have a good answer to that yet. I can say the following: haloscopes won't work because the volume is so small that basically these kind of approximations are not well justified. So it's not well justified to use the Hartree-Ansatz to kind of describe really this extremely small volumes of haloscopes. So it's so I just. For that, we just don't have a good answer. I would have to go beyond, and it becomes, then it's not this pure, beautiful single mode squeezing. It's something else. But I do assume that there is some remnant of that kind of remains in some form, because you have this nonlinear. Effectively, you have a nonlinear evolution, and in principle, it creates some kind of quantum features, unless you decohere it. So I don't know about the haloscope, but I think there could be relevance in principle. What basically this means, the squeezing, is that your noise that you associated with the system is kind of larger, I think, than you would expect. And so I wonder if there's maybe some way to kind of look at that, or maybe that matters, that is kind of effectively very noisy, whether that matters for maybe some of these structure formation arguments or so. And so my short answer is I don't know, and my longer answer is I think there's a few ideas, and I think that's really that's really the most interesting questions about this.
Thank you. Alexander?
Hi, Igor. Very nice talk. Thank you. This was really creative. I had sort of a similar question to the last one, but I think you did a good job answering it. I have two questions. What controls the quadrature that the squeezing occurs along? Like in what direction in phase space is it squeezed? Because that might affect the implications of the noise model. And then the other thing was, I just want to make sure I understand the way you're using quantum in this context. It's because the usual classical analysis doesn't take into account this nonlinearity, which would produce this additional squeezing effect. Is that right? Just not a witness seeing squeezing by itself wouldn't necessarily indicate a quantum thing or something, but it's the fact that you have this explanation from this interaction.
Yes, let me start with the second question, which is conceptual. Yes, you're absolutely right. So of course, coming from quantum foundation, think about it. There's a huge spectrum of what we mean by quantum versus classical, and and it's it's very unclear. It's a lot of semantic. However, you're absolutely right. What we wanted to say is the following, namely, well, if your state goes beyond kind of a coherent state into a direction of kind of a squeeze state, then let's use that as a benchmark to kind of signify that, well, your pure classical description is kind of inadequate. You could, of course, still, say, well, there is some classical description, but, in the sense of, that you don't have a positive P function anymore. So it's kind of like as a way, not necessarily to say like how quantum really it is deeply, but it is, it is already kind of, much more quantum than you would expect from like just a classical kind of, a fluid argument or so. So you're right, but it's not, we didn't go beyond squeezing. So that's why I briefly flashed it. There is like even a real quantum timescale when you create superposition states. That's kind of, really, really, but that's much, much longer. So it's kind of, there's this Jurke-Stoller result where first you squeeze, bananify the state, and at some point there are superpositions that arise, but it's much, much longer timescale. Plus, of course, it will kind of decohere beforehand in some way. So we didn't go that far, but it's more in that sense, kind of a little bit quantum. Let me put it this way.
No, I don't mean to give you a hard time. I think it's exactly right. Yeah.
No, but you're right. So it is a subtle question, even in many ways, and that's why we thought kind of from a quantum optics perspective, maybe there's something very concrete to say. But to your other question, it's an excellent question, and you know what, I don't exactly remember because this was the calculations we did 2 years ago. So the thing is that I don't think there's anything that can specify the direction in which you squeeze, because intrinsically you have an n squared interaction. I mean, in a Hamiltonian. So I don't think it singles out a specific direction. So I don't remember if this was in a in a rotating frame or what happens. I have to look it up again. Sorry about that. But but one has to be a little bit careful with this kind of squeezing approximation to the full Kerr oscillation. So n has to be still preserved, and then this angle. I think it's not. There's no squeezing angle that's actually well defined. That's why I think it will become kind of just some kind of noisy.
Okay, sort of rotate. Okay, all right.
I think you're rotated, but I'll have to refresh myself.
Yeah. Thank you.
Okay. So thank you very much, Igor, for your beautiful talk. I think we have to continue. The next speaker is Leo Holberg from Stanford University, and he will present results on quantum magnetic imaging of magnetic field contours. Please, Leo, the stage is yours. Very good. This seems to work, but we cannot yet hear you. So we are not hearing you.
Leo, you need to unmute yourself.
Okay,
yes.
now do you hear me?
Now it works.
All right, sorry. Well, we're getting set up. We're running a little behind schedule. I can try to speed up, or what are we? What's our goal?
Don't worry, it's fine.
Okay. All right. First of all, I'd like to thank Olga and other organizers for the opportunity to present some of the work we're doing here at Stanford. And it's been a long time since I've been to the laser physics workshop. Happy to reconnect with people around the world, and we're fortunate now that we have these electronic Zoom and other ways to communicate. Even in difficult times, we can communicate around the world without having to travel and things. So thanks for this opportunity. The work I'm going to describe started off with work we were doing on ytterbium atoms for an optical clock. And ytterbium's an interesting atom for many reasons, as we've seen in other talks. It has some narrow clock transition. It has a good cooling transitions, first stage cooling, second stage, and some interesting transitions also for quantum networking, because these two colors go through optical fiber. So there's lots of groups working on that. We've been exploring some of the clock aspects. And the people really that I want to highlight that are doing the work, most importantly, Hongxuan Li, Tina Nanarong, and Josh Tong are the grad students working on this. And they're the ones that have done most of the work and discovered the physics that we're going to explore. But today I'm going to talk about quantum imaging of magnetic field contours using these ytterbium atoms. And so we're going to simplify this system to a nearly two-level system, actually 4 levels, and just a single laser. And we have to say quantum these days, even though this is just atomic physics. It's not quantum 2.0. There's no entanglement. There's no squeezing. This is just known atomic physics, but I think a unique, compelling magnetometer that gives results that other magnetometers don't. So what we were trying to do that started this work was, my contention is we now have these optical clocks that are essentially perfect, 18 digits or 17 digits. And if we're going to call it a clock, I think it has to keep time. It's not just a frequency reference. And if you're going to keep time, you need to be able to synchronize it. You need to know where it is in some known reference frame, and you need to be able to distribute the time. And that's, I think, the reason why these optical clocks have not really changed worldwide timekeeping at all. We can get timing to about 10 nanoseconds anywhere on the Earth through the many GNSS systems. And that really hasn't improved, even though the optical clocks are 10 to the 4 or more times better in both stability and in fractional frequency uncertainties. So we've been trying to simplify the ytterbium. thinking that we could use a single green laser for stimulated force cooling to load a mott and a clock. So we wanted to make it into a 2-laser clock. I think to address these other issues I talked about, the clocks have got to be in space, or we have to have links to space. Otherwise, we're not going to make an impact. So that's the motivation. But what happened was, so this is our experimental system. So here we have, can you see the cursor? Atomic beam there. This is a transverse cooling or pushing region. We were going to use pulses to deflect the beam, and this is the mott. This is a large coil that makes the magnetic field gradient for the mott. So everything I'm going to talk about is in this region in this talk. None of the rest of it's going to matter. So this is the experimental system. We have a ytterbium oven. The beams are going in the plus Z direction, and these axes will be important later. The laser is going in the plus X direction, and we square wave modulated or pulse modulated or sine wave modulated. Single laser crossing the atomic beam. The laser is a sheet now. It's 3 millimeters tall and 30 millimeters wide. And all of the data that I'm going to show is just taken with a simple camera looking down on the fluorescence in the atomic beam. Since we have this big magnetic coil over here, there's a strong magnetic gradient across this region, as well as can be a strong magnetic field. So again, atoms go along Z, B at least initially is along Z, and B gradients along Z. And if you look from the top, one of the students, Hong Xuan, said, I see these funny dark stripes in the fluorescence. And these dark stripes depend only on the magnetic field, and they don't depend on the laser tuning to first order. They do depend on the modulation frequency. So we spent a little bit of time going around what might these be, and this is the configuration. If you have modulated light, you have more than one frequency present. And we'll do some analysis here. We'll go through some analysis just assuming there are two, but for square wave modulation, you got several harmonics. But it turns out that when any two of these match the Zeeman splitting in the excited state, the system goes dark. And now we can ask the question, is this CPT? Is this electromagnetically induced transparency? Is this Outler-Towns, or is it something else? And so we've done some analysis. And I'll try to walk through that in a little bit, but I want to emphasize the simplicity. Single laser, single atomic beam, and modulated light, where we know the modulation frequency directly because it's done with our RF source. So if we have this 4-level system, we've got a singlet S0 ground state, no structure, triplet P1 with M projections along the quantization axis, and you apply a magnetic field, you get a Zeeman shift, not surprisingly. The transition on the second stage cooling is kind of narrow, not super narrow. It's 180 kilohertz wide. It has a fairly low saturation intensity, only 138 microwatts per square centimeter. And so when you apply a magnetic field, it splits, and if you apply the laser field polarized along the y-axis, and if we make the assumption that the magnetic field's along Z, then the electric field can be decomposed into the linear polarization can be decomposed into sigma plus and sigma minus. And if we have two laser fields, just say two sidebands, when two of them match a transition, we have this V configuration. And if the power is strong, we get AC Stark splitting, the Outler-Towns splitting at the Rabi frequency on these 3 levels. So then if you calculate the fluorescence, well, let's see, there's also the symmetric case for when the field is in the opposite direction. The +1 shifts down and the -1 splits up. So we've got 2 resonant conditions for 2 laser fields and 2 magnetic fields. And the analysis is just based on a Hamiltonian that has the 4 energy states, the ground state, the +1, M1, the M equals 0, and the -1. In the rotating wave approximation, we still have these detuned laser fields from omega-1 with a detuning delta-1 and omega-2 with a detuning delta-2. And so this is what the Hamiltonian looks like. And this work was done primarily by Tina Nanarong as part of her thesis work. Solved this using these nice Q-tip density matrix master equation, and include the fluorescence decay by from these collapse operators. Now, one thing that's interesting about ytterbium is that this state has a lifetime that's something like a microsecond, a little less than a microsecond, 875 nanoseconds. And so the atom decays, but it's easy to have it in a strong field. We only need, say, to be 10 times above ISAT, we only need a milliwatt per square centimeter of light intensity. So for that case, so here's the case where the Rabi frequency on both omega-1 and omega-2 is 10 gamma, where gamma is the natural line width, and the modulation frequency is 20. So this is for a single atom at rest, driven by the two laser fields. And this is the fluorescence, calculated fluorescence as a function of the magnetic field. When the magnetic field gives a Zeeman shift that matches the modulation frequency, you'll get resonances. In the low field limit, they're just Lorentzian lines. So the Lorentzian lines become these outward towns. And this is the total fluorescence intensity. This is absorption. We don't measure the absorbance, but this is the fluorescence intensity. So this is outward town splitting, two lines. And one of the interesting things about this is that the laser, the natural width of the transition is, again, about 200 kilohertz. The Doppler broadened in the transverse direction across the beam is still 5 megahertz. So it's Doppler broadened even transverse to the laser beam. But when you do the Doppler average, you get dips in the fluorescence. That doesn't wash out the dips in the fluorescence. So the Doppler gives you some fluorescence across that profile, but we still get these 3 dips. So the model seems to agree with the data in terms of producing these dips at the resonances when the modulation frequency matches the Zeeman splitting. So that's beginning to look like an interesting magnetometer, because well, here's a case where you have just 2 frequencies and you have a dip at 0, which in fact is partially due to the Outler towns and partially due to the Hanley effect, which I'll mention in a second. And then a dip when the difference frequency, when you put more sidebands on, like modulated light, then you get more and more dips. And so this is showing if you're modulating at the laser intensity at, say, 1 megahertz or 2 megahertz or 4 megahertz, the position of the lines, the dark lines, agree then from the different modulation frequencies. So this is telling us that we're beginning to measure the local magnetic fields with radio frequency precision. And the theoretical model is at least semi-quantitatively in agreement. We've got a lot more than this now, but we've got reasonable agreement for the theoretical model and the experimental data. So again, we have when the modulation frequency equals a Zeeman splitting, we get a dark line. Okay, so this is going to illustrate another reason that I think this is actually going to be useful. So if you just hold a magnet outside the vacuum chamber and wiggle it around by hand, this is what you see. So here we have the gradient along the Z direction, and the dark stripes are going here. You can see those. This is when the laser is intensity modulated at 1.2 megahertz. That means the splitting between the magnetic, this is a contour of constant magnetic field. And here's the next one. Those are split by 0.299 Gauss. And if you just hold a magnet near it, you can cancel the magnetic field. This turns out to be the zero field and is even darker because of the Hanley effect. So I'm going to show a little video just to show, because we think the response time of this ought to be 10 microseconds. So if you wiggle the little magnet around, this is what you see, and you can see it by eye or you can see it with a cell phone, and you're measuring the magnetic field in real time in 2 dimensions. The spatial resolution is limited along the beam direction by the decay time of the atom to about 100 microns, and transverse it's about 15 microns. So here you can get 15,000 measurements of the magnetic field known with RF precision over an area from about, this is about 3 centimeters by 1 centimeter. And so we've been trying to understand this in some detail now, and we've got a paper mostly written up to describe this and will be submitted soon. I think it's going to be useful. Oops, now it's going again. This should jump to the next slide here. Here we go. So if we just take a slice through the image with this yellow line, you can plot these dips, and from the dips you can count off the magnetic field. And here's an example. One thing you'll note here is the zero dip is much bigger than the other harmonics, and that's due in large part to the Hanley effect, which we came to understand from a paper we found subsequently. Dallin Durfee and group had looked at strontium on the singlet P1. Okay, so let's see, where are we now? Yeah, so this is, if you just map out those magnetic fields as a function of the modulation frequency or even from a single image, you get in a short time map a single image. For us, we get a frame rate of 300 hertz. So in 3 milliseconds, you get the whole image in the 2D magnetic field. And with about 1% uncertainty. So I don't know other magnetometers that can do this, and I kind of like this compared to what I saw as a child when you used magnetic filings in a magnet. You could see, and literally you can see this by eye. Here's some comparison of the theoretical model that Tina has done with Hongxuan's data for linear gradient and pulse modulated light, where this is the Fourier spectrum of the light going in. And so this is as a function of laser power. So at low laser power, you don't see the dips. And as you increase the laser power, where this is only milliwatts, so this is 16 milliwatts of power, you see these dips becoming fairly prominent in the fluorescence. Okay, so now I want to talk a little bit about why this can be a vector magnetometer, not just a scalar magnetometer. So up to now, we've had B field in the Z direction and electric field in the Y direction. But we can rotate that polarization, and you can rotate it quite quickly. And then you will be able, if you get E parallel to B, then you have only pi transitions in the dips going. And this, we've got theory that goes between these two, and that's assuming that there's only a Z magnetic field. But if we have a little bit of Y or a little bit of X, what's going to happen to these dips? So just I'm going to skip this. This is if you just rotate the polarization for that case. So now I want to treat the case that we have, whoops. So that's all the same so far. So now I want to treat the case when we add additional magnetic field directions to the Z direction. Whoops, this is not going. So this is only Z as a function of angle. So this is what the fluorescence image, this is the calculated one, fluorescence image for a linear gradient, just rotating with no Y or X component of the magnetic field. if you add some by, now these curves change. The by and the bx at theta equals 0. 0 is along the z-axis now. So now we switched x and y. And then if you go in the 45 degrees with the polarization, the central lines begin to move and some don't. And we've got a pretty good model of this now that can now tell us how much of bx and by do we have by simply rotating the polarization. So we can get bz, bx, and by. We cannot tell whether it's plus x or minus x with one direction, but with another laser beam, one could get all three components and know the sign of those. So let's see if I want to, the thing I want to point out about this. This is what one of those moving dips might look like as you rotate the polarization from 0 along Z up to 90 along Y. And our theoretical model now looks pretty close to this experimental data. And this is for cases where we have a Z gradient and an X and Y of comparable magnitude. Okay, so let's see if there's anything else. I've got a little summary slide here. This is a pretty broad transition in terms of magnetometers. You know, if you compare it to cesium or rubidium magnetometers, the line's about 100 times broader. And so the sensitivity is going to be 100 times worse, but the dynamic range, we think it can go up to 10 kilogauss and it goes all the way to 0. I think usefully we can measure from sort of milligauss or 100 nanotesla. And I don't see why we can't go to many Tesla, but we haven't done that. And it takes a second laser if we want to have that much tuning. We get 15,000, even with the simple system now, 15,000 spatially resolved B field measurements in 3 milliseconds. And the response time of the atom is 10 microseconds. So I'm optimistic that this could be a dynamic magnetometer that could do 3D magnetic tomography in real time at video frame rates. So we're having a lot of fun with it. It started out as a clock and now it looks like it's a magnetometer. Let's see if there's anything else. Can do both scalar and vector. And it's only a single laser and a modulator. You could modulate up to gigahertz speeds. If we want very high magnetic fields, we'd need another laser. And pretty low power is required. So that's another advantage. So you can also not move the magnetic field, but tune the frequency. So this is if you change the modulation frequency, you just map out the field and quickly. So anyway, we're enthused about it, and I appreciate the time to present some of the work we've been doing here at Stanford and looking for good opportunities for 3D imaging of fast magnetic fields. Thanks.
Thank you very much for this beautiful results. I can understand that you're enthused with these nice images. And well, what questions do we have in the audience?
Leo, as far as I understand, it is extremely sensitive as compared to what was done in rubidium and in some solid systems. But as a matter of principle, is it somehow different? Because this kind of EIT and Stark effect, they've been used, for example, you know, some work for the vector magnetometry was done recently, for example, by Irina Novikova, Dima Butker. Is it something different?
You know, we thought it was the CPT or EIT, but it's really, this is primarily Outler-Towns AC Stark and Hanley effect. In the V system, the plus M and the minus M are orthogonal, and we can't get EIT. The Hanley effect, though, does have quantum coherence between the two. So those two are similar.
They are very similar, in fact, yeah.
Yes, but these are orthogonal states. So the dominant, we believe the dominant effect in this case, because if I go to low power, the EIT should still persist, but the Outlier towns decreases. And you may have seen the slide where the contrast on the dark line resonances depends fairly strongly on power.
So low power means interference plays a role, of course, yes.
Yeah, right. So, maybe we're wrong, but the model's doing pretty well so far. And the other thing is there's no optical pumping in this system, where in rubidium and cesium, there's lots of optical pumping, but this is a singlet S0 ground state. So there's no optical pumping.
I see. Thank you.
The caveat on that is if we went to the odd isotopes, there would be optical pumping. So lots more to be explored.
Thank you.
So, more questions? So I have a question. What would you do to improve the resolution or the contrast of the signal? Do you have to prepare light sheets of the laser in a specific way, or do you have plans?
So I think we have plenty of contrast now to make real measurements. What I would like to answer, there's several questions I would like to answer, is how well can we determine the vector orientation? We know that we have some X and some Y, but what's the uncertainty in that? And I would like to understand the dynamics. Can we really measure pulse magnetic fields and induced currents and rapidly changing fields at video frame rates over 3D dimensions? So those are the things I'm going to focus on, because I think if you just wanted to try to compete on sensitivity or something, if you don't take into account the spatial resolution and the dynamics, I think that's the unique part of the ytterbium system.
Okay, thank you very much. Well, I do not see any more questions, so let's thank our speaker again, Leo, and we will move to the next talk by Andrew Geraci from Northwestern University. He will describe his work on ultrasensitive force measurements and searches for new physics with septonewton forces. Thank you very much, Andrew. The stage is yours.
Okay, thanks very much. Let me just switch to the right presentation mode here. I'd like to thank Olga and the organizers for the invitation to speak at this very interesting conference. I think I have to switch my display here. Sorry for the delay. Can people see the full screen version?
Yes, we can see it.
Okay, excellent. Controls. Okay. Okay, yeah, so I'd like to talk about some of the work we're doing using radiation pressure to suspend dielectric particles, and then using these particles as highly sensitive force measuring devices. And I'll talk about some of the physics applications that we're interested in doing using these particles in these systems. So if you look at the work we're doing, it is part of the relatively recently expanding field known as levitated optomechanics, which really goes back to early work by Art Ashkin and collaborators back in Bell Labs in the 70s, where they developed techniques that eventually led to things like optical tweezers, which has had a major impact in fields like biology and biophysics. And also, of course, that work led to a lot of the work in laser cooling and trapping of atoms that has formed now what we know of as the modern field of AMO laser trapping and cooling. And so most of the work Ashkin did originally was done in the context of water, although he did some experimenting with holding particles up in high vacuum as well. And so the basic idea is that you have a dielectric particle. It's a polarizable medium. So like you have basically Maxwell's equations. You have some dipole moment induced in the material due to the electric field of the laser. And you naturally get an interaction where you essentially have a high field seeker, where there's potential minimum if the particle is, say, trapped at the focus of a laser beam. And if you had, for example, a spherical particle, you can confine the particle basically in 3 dimension and essentially realize 3 decoupled harmonic oscillators of the particle moving around in this optical potential. The sizes of the particles that can be trapped range over orders of magnitude from, say, tens of nanometers up to tens of microns. And sort of depending on the size, you can think about the interaction as sort of occurring in the dipole limit or sort of Rayleigh regime for small particles. Or for larger objects, you can really think about it sort of as the ray optics picture of the refraction of the light, which is responsible for the confining forces in these kinds of traps. One of the key features here of this sort of holding up objects with only radiation pressure is that you can very well decouple them from the surrounding environment and realize very high mechanical quality factors with very little mechanical dissipation from the surrounding environment. And there are techniques people have now demonstrated to cool using laser feedback cooling or other cavity cooling techniques to essentially reduce the motional temperature of these objects by to an extreme degree, where in fact now the ground state of the art is that now using a couple of different methods, different groups have demonstrated cooling of the particles all the way into the motional ground state of various trapping configurations. So in addition to being an interesting system to study to realize this quantum behavior of the motion of these objects, the extreme environmental decoupling that one can achieve here also lends itself to the possibility of very highly sensitive force measurements. And so you can look at the projected force sensitivity of these kind of devices. So, for example, for a spherical particle of sizes here ranging from tens of nanometers up to tens of microns, you can look at the minimum detectable force that you can measure due to the interactions with the thermal environment at some temperature kT. So for example, a room temperature environment in an ultra high vacuum where you have very little background gas collision, say at 10 to the minus 10 torr, depending on the size of the particle, you can see that, say, for micron sized particles, you can measure forces here that are on the order of 10 to the minus 21 newtons per root hertz, or in other words, zeptonewtons per newton hertz. You can also look at the acceleration sensitivity on the right axis here, and for the larger type of objects, you can get down to kind of nano G per root hertz level acceleration sensitivity in these kind of systems. Already back a decade ago, some impressive results were seen for inferred force sensitivities at the several tens of zeptonewtons per square root of hertz. There's a little bit of deviation you see on the right side from this straight line, which is just due to the thermal noise. And this is due to quantum noise from light scattering. Essentially, you have Rayleigh scattering of the trap laser photons, which basically causes a recoil on the motion of the particle. And due to the discrete nature of photons, there's a random process involved there, basically leading to some momentum diffusion or heating mechanism in the motion of the particle, which does affect the ultimate force sensitivity that these kind of systems can realize. But you can still see that over quite a large range of sizes, it's possible to get to extremely low force sensitivity. Other highly sensitive force sensing devices, for example, microfabricated cantilever beams, tend to be a few orders of magnitude worse in sensitivity, something at sort of attonewton or 10 to the minus 18 newton per square hertz level. So there's a few different ways of realizing these kind of devices, and loading these nanoparticles into optical traps. And so in our lab, what we do is essentially we have a substrate that we coat with a set of nanoparticles. In this case, this is an example of one of the devices we're trapping. One of the types of particles. It's a 300 nanometer diameter silica glass particle, and we basically shake a piezoelectric substrate, and a shower of these nanoparticles rains down on above an area where we have an optical trap with a focused laser. So in order to shake off the particles, however, with such a small size, you have a very strong van der Waals interaction you have to overcome. And in fact, you need an acceleration that's on the order of about 10 to the 7 Gs to have the particle actually get released from the surface. And so here's a little movie of kind of one of these devices in action. So you can see here there's kind of a rain shower of particles, and if you look closely, you can see there's one particle here that made its way and actually is stuck in the focus of the trap. And so we typically are loading these particles in a situation where we're basically at a few millibar of background gas of nitrogen. So there's a little bit of damping so that if the particle finds its way into the minimum of the optical potential, it will stay there rather than just simply ballistically flying through and coming out the other side. However, if you want to realize this really high force sensitivity in environmental decoupling, you have to remove the background gas. And so you can stabilize the particle basically by using laser feedback cooling as you evacuate the air or nitrogen from the chamber to then realize the high vacuum limit. And so here's one of the setups in our lab where we have counter-propagating beams that create an optical standing wave trap or a 1D optical lattice, if you like, where we can catch these nanoparticles. And then we've shown that in the high vacuum limit, you're very well environmentally decoupled. In fact, you can do force measurements down at the level of a few zeptonewtons or 10 to the minus 21 newtons with these systems. And so to calibrate that, we took advantage of the fact that about 10% of the time in our setup, at least, we tend to trap a particle that has a non-zero electric charge, either one or two excess electrons. And so then if we apply a known electric field, we can apply a known force and then use that to calibrate the system. And so this level of force sensitivity is significantly improved compared to other kind of solid state, at least room temperature types of force sensors. And so we're interested in using this to do a variety of different experiments looking for new fundamental physics. And so I'll just say a little bit about some of the different experiments we're doing in the next last 10 minutes or so of the talk. So one of the things that's really motivating us to look for new physics, if you look at the standard model, it does a very good job of explaining the fundamental particles and the four known forces in nature. And in fact, if you look at some recent work from my colleague here at Northwestern, Jerry Gabriels, they've done another improved measurement of comparing experiment and theory by looking at the electron's magnetic moment, where now one can compare theory and experiment at the part per billion level and show perfect agreement with the standard model. So despite this amazing predictability and remarkable agreement with theory and experiment, there's really a lot of unsolved mysteries that the standard model can't account for. So the elephant in the room, if you want, is that about 95% of the universe is unknown in terms of what it's made of. We don't know what dark matter is. We heard a nice talk by Igor on that a little while ago. We don't know what dark energy is. It's embarrassing how wrong we are about how large it should be if we use the same theory that gives us this remarkable part per billion agreement with the standard model parameters. And then also we heard a little bit as well earlier in the session that we don't know so well how gravity works in the context of quantum mechanics. And in particular, some of the work we're using these nanoparticles on is hoping to shed some light on that last topic. And so to further motivate those experiments, if you look, for example, at the relative strengths of the known forces in the standard model, and say zoom in inside of a nucleus and consider two protons that are sitting close to one another, if you kind of normalize the interaction so their electromagnetic interaction is one, the gravitational attraction between the two protons is about 36 orders of magnitude weaker than the electromagnetic interaction. And so this is basically an artifact of the extremely large difference in the energy scales of gravity versus electromagnetism. And so theoretically, it's known as the hierarchy problem, and it causes a lot of fine-tuning in order to explain, for example, why the Higgs mass is what we've now measured in the Large Hadron Collider. And so there are many theories beyond the standard model, for example, supersymmetry or other theories that suggest that we should see some new physics that explains this mystery and eliminates the need for these extreme fine-tunings. And one way to measure that, in addition to doing accelerated experiments, is to do a precision measurement of gravity at very short distances. And so in particular, some of these theories where you have new physics solving this mysterious hierarchy problem will give you new corrections to the Newton potential. If I have two masses separated by some distance r, I have the familiar freshman physics form here on the left, and then inside the parentheses, we have some new term here. So there's some new physics with strength alpha relative to gravity. So alpha is some dimensionless number, and then there's some range lambda, which is basically the Compton wavelength of some new particle that's responsible for this new interaction. And so, as I was saying, things like supersymmetry or string theory, or other ideas like, for example, there could be particles in large extra spatial dimensions, for example, give you theories where you might expect at the sub-millimeter range to see some interactions essentially turning on at those distances. And this also can be looked at in many cases as a violation of the equivalence principle, or looking for a new kind of fifth force, which would show up, but only at short distances. And so while this 1/r form of the Newton potential has been really well tested at planetary scales and Earth-Moon distances by, say, lunar laser ranging, if you looked at the laboratory scale at micron-type distances, in fact, you could have forces that are 1 billion times or higher, stronger than gravity, but there'd be no experimental limits that would otherwise preclude that. And so the challenge there has to do essentially with the weakness of the gravitational constant, or in other words, the high energy scale of the Planck energy, where basically you have, if you just have material around that's, say, as dense as you can find on Earth, and you say take two spherical masses and bring them together as close as possible, you can study how the force scales with the size of that system. And if you shrink things down, plugging in the fact that the mass of each object has some is due to the finite size and density, then the Newtonian force between the two spheres scales like the positive fourth power of the size scale. And so this gets weak very, very quickly as I shrink things down into this experimentally interesting range of distances motivated by these theoretical models. In particular, if you have if you're interested in looking at interactions at sort of the 10 micron length scale, then the force you have to measure is this 10 to the minus 21 newtons or zeptonewton level forces, which is basically about equivalent to the weight of a heavy molecule in the Earth's gravitational field. So it's an extremely small force that's very challenging to measure. And on top of that, you have to contend with the fact that you have very strong background forces from, say, electromagnetic effects, including things like the Casimir effect, which is interesting in and of itself, but can be many orders of magnitude stronger than gravity when you get objects separated by kind of micron type distances. And in addition to that, you can also have spurious electromagnetic interactions, for example, from things like patch potentials. So if you have a conducting surface even with a uniform metallic film, you can have polycrystalline grains of the conductor with different work function variations over the surface, and therefore local potential differences over the surface, which can also lead to spurious backgrounds in these kind of experimental investigations. So if you zoom in on that kind of shorter distance end of that parameter space now, looking at kind of micron, ranging from 100 microns down to 10 nanometers, and on the vertical scale, I have that strength parameter here relative to gravity. The area in yellow is what's been ruled out by experiment. This is primarily due to mechanical oscillator type experiments like the torsion balance experiments that are at the University of Washington. There's also been micro cantilever experiments, and as well as experiments that are adaptations of Casimir type measurements. And so the region on the left with the shaded regions is some of the theoretical predictions for where one might look for new things. But so these all have some sort of mechanical force center, and their force sensitivity is limited by fundamentally by the same thermal noise I mentioned at the beginning of the talk. And essentially, you have some thermal bath in contact with your oscillator, and from the acquisition theorem, you can figure out that there's some minimum impulse or perturbation you can measure on top of those random thermal kicks due to that kind of temperature. And that minimum force you can measure looks like the thermal energy KT times the spring constant times the measurement bandwidth over the product of this mechanical quality factor and the frequency. And so here's really where this using radiation pressure to suspend a particle and act as a force sensor, it gives you an advantage. In a solid system, for example, like a cantilever, the mechanical quality factor is limited by clamping and surface loss and that sort of thing. And so by suspending the particle and watching the center mass motion of the particle in the laser trap, now you can decouple that motion from these lossy mechanisms from the materials and the clamping and so forth, and now realize a potentially much improved measurement. So in our lab now, we're working on one experiment is to look for inverse square law violations at micron range distances, where now our test mass is actually one of these laser suspended silica particles. We suspend the particle in a standing wave that's formed near the surface of a mirror. And then behind the mirror, we have a device that we move up and down to modulate the gravitational interaction with the particle. And so in our case, the device has teeth of gold and silicon, and it moves on a movable element. And so as we move the device up and down, we basically modulate the gravitational force due to the variation, the density of the gold and the silicon. And so by trapping the particle at the closest antinode to this very thin silicon nitride mirror membrane, which is at only a few hundred nanometers from the surface, we estimate that we should be able to, with this level of sensitivity that we've seen, get several orders of magnitude improvements in terms of these searches for new physics at that micron length scale. There's also similar work operating at a bit larger length scales and using a slightly different geometry that's ongoing at Stanford and as well as at Yale. So in our setup, we have two counter-propagating lasers that form a common focus where we trap a nanoparticle, and then in order to get the particle right up against the surface, we have a microfabricated mirror membrane that's a retroreflector that has a sharp knife edge on it, and we basically cut into the laser beam using the knife edge, and then depending on where we choose to position the membrane on a stage, we can determine at which antinode the particle gets loaded in next to the surface. And so the closest position that we can trap it here is a quarter wavelength, which is the first bright spot of the laser beam. The source mass is this section material of gold and silicon, where basically we use a silicon wafer, etch pits in it, and then deposit gold. And then after we do that, there's still sort of a remnant of this periodic deposition of the gold from the trenches that we had in the wafer. We don't want that because we don't want the electromagnetic forces to be modulated at the same period as the density modulation. So essentially what we do is flip this thing upside down and polish the silicon away from the backside, leaving only a flat surface. And this is a cross-section cut using the focused ion beam showing the middle of that process. But this basically allows us to present a flat conducting plane surface behind the mirror, which should suppress the variations of electromagnetic effects and leave only the density modulation to drive the motion of the particle. So some results on loading the particles near the surface. So here is some earlier work where we showed you can basically take a particle and create this retroreflected optical lattice trap, depending on where you choose to insert the mirror, that you can control how far from the surface the particle sits. This is a picture of the motional spectral density of the particle before and after we insert that mirror membrane. You can see when we insert the mirror, you have the standing wave giving you a much tighter confinement and increasing the frequencies of oscillation of the particle. And then we showed that you can control the separation from the surface by determining at which point you slice the mirror in. And then you can also use stages to scan the particle over the surface and basically map out the force profile near the surface, and we think this will be quite useful for looking for these patch potentials and other backgrounds, which are going to be really important. So I just want to very briefly mention that we're also looking at developing these type of techniques to look for other gravitational physics, in particular gravitational waves at higher frequencies than the LIGO detectors are looking. I don't really have time to explain in detail since I'm kind of running out of time here with my allocation, but essentially what we want to do is extend the frequency range above where the LIGO type detectors work, look for dark matter related motivated sources like axions and primordial black holes. And so we're building a prototype to test that. I'll skip over some of the work we're doing there, where we're trapping some fairly large objects, now not just small spherical particles, but large plate-like particles, which have advantages for this gravitational wave application. In the longer term, it's possible to think about using matter wave interference type experiments. We had a nice talk by Ron Fullman earlier. We're trying to realize a demonstration where we can actually show diffraction of a nanoparticle as a matter wave off of light grating. If one can do this, it's sort of a step towards the experiment that Ron mentioned also earlier, potentially using these nanoparticles as fairly massive systems to try to study the gravitational field that's actually produced by a quantum superposition of these nanoparticles. And so this is, I think, an interesting future goal for this community in this field. And so with that, let me just summarize. So we've shown that you can do high sensitivity calibrated sensing with these nanoparticles, and we're looking at various gravitational physics applications. In the longer run, I think it's interesting to think about other tests of gravitational effects and entanglement and other tests of fundamental quantum foundations. And let me just acknowledge my group, the people doing the work, and thanks everyone for your attention.
Thank you very much, Andrew, for the great experimental results and the progress in using nanospheres for detecting everything, including gravitational waves. Are there questions?
I kind of had a quick question. Maybe it's naive, but can we use these levitated particles for making torque measurements as well? Or is it just force, or is there something that prevents that?
Yeah, that's a great question. And so there's some really nice work by Tongtang Li at Purdue University where they've done some experimental traps of nano dumbbells. Basically, you have essentially a rod with two balls on the end of it, and you can spin that, and you can do amazingly good force torque sensitivity with these systems as well. So yeah, so that's already been looked at a little bit. And I think he has ideas of testing things like Casimir friction and other sort of novel effects near surfaces using those devices.
And now that you're able to trap these hexagonal plate ones, they have different moments of inertia, I'm assuming, too, so you can play these kind of games. Oh, cool. Thank you.
Sure.
Leo?
Nice talk and interesting work. For the gravity waves, how do you deal with the seismic noise on the Earth?
Yeah, it's a good question. So if you look at our plot, we're actually, above the band where LIGO operates. And so most of the seismic noise and gravity gradient noise problems that LIGO worries about are kind of, the tens of hertz and below sort of range. So because we're at 100 kilohertz, we're lucky that we don't have to worry so much about those. We still need to worry about things like thermal noise and mirror coatings and things like that. But we think we'll be most likely limited just by the motion of the particle itself.
Okay.
Great, thanks.
Okay, I do not see any more questions, so let's thank Andrew again. And we'll proceed to listen to Alexander Smith from Dartmouth and St. Anselm College, who will speak about information theory, and in particular, quantum time dilation, a new test of relativistic quantum physics.
Well, thank you very much, and thank you, Olga, and the organizers for inviting me. I'm really happy to share this work with this audience. This is stuff I've done with my close collaborator, Mehdi Amadi, who's at the University of Santa Clara, Andrzej Dragan and Kasper Debski, who are at the University of Warsaw, and Peter Goczewski, who's now at ETH Zurich. So what I want to do in this talk is really tell you about three different things, and in the third, how the first two sort of all come together. So the first is I'm going to give you a quantum description of clocks from a metrology perspective, namely as a parameter estimation problem, and introduce to you what I mean by time observables. And then the second thing I'm going to do is introduce a relational notion of quantum dynamics. That is, when we have two physical systems described by Hilbert spaces and quantum mechanics, how can we use one as a clock and the other, the other system here? How can we use the clock to track that system's dynamics without postulating any background time structure? And the motivation for this is really coming from a quantum gravity perspective, and I'll use the notion of clocks I introduced in the first part of the talk to do that. And then combining these two different aspects, I'll use them to describe this quantum time dilation effect to basically ask the question, if I have a clock and it moves in a superposition of two different momenta wave packets, what would be the time dilation it would see relative to another clock? And in here, I'll talk about maybe some potential experiment that we might be able to actually witness this effect. So with that, I want to start with answering the question, what is a clock? And it's a physical system. So, and it's going to be described by quantum mechanics. So it better have a Hilbert space. It's associated with a Hamiltonian. When we build the clock, we prepare it in some initial state. So there'll be some fiducial state associated with our clock. And then there's going to be a time observable, and I'll define that in a bit more detail in a second, that we can use to measure the clock, and that'll spit out the time for us read by the clock. So, okay, so what happens when we try to measure time? Well, we prepare our clock in this fiducial state, row C, and then time happens, and what happens is the amount of time, I'm calling here tau, gets unitarily encoded into this fiducial state. So that at some later time tau, the state of the clock is row C of tau, right? So then the question is, well, what time observable should we measure on row C of tau to best estimate the time tau that it indicates? Yeah, so this is a very metrological way of thinking about clocks and estimating the time. It turns out that, if you think about it for a little bit, there's two criteria you would expect of this time observable, is that on average, this time observable when measuring row C of tau, it should estimate the elapsed time tau. And the second is the variance in this time observable shouldn't depend on the time tau you want to measure or want to estimate, right? And this is what we mean intuitively by a time observable. And it turns out that these two criteria spit out for you what this time observable should be. So I want to go through that in a little bit of detail here. So this time observable is going to be described by what I call a POVM, a positive operator valued measure. So usually we think of observables as associated with self-adjoint operators, and I'll explain how that connects, but this is a slightly more general notion of an observable. So what it is it's a map from a set of outcomes, in this case tau, the different outcomes our clock could indicate corresponding to different times read by the clock, to a set of an effect operators that are these one-dimensional projectors here, defined in terms of what I'm calling these clock states here. These effect operators, they satisfy a bunch of nice properties. They have to be positive, they have to add up nice, and they have to be normalized, which just ensures when we use the standard Born rule, we get a well-defined probability distribution for the time read by the clock. So here's just if we want to know what's the probability of our clock reading time tau, and the state of the clock is row C of tau prime, well, then we take the corresponding effect operator and take the trace, and that's the Born rule. And that'll give us a probability for outcome tau. Now, I've just told you what a positive operator value measure is. What makes it a time observable, namely one that satisfies those two previous properties, is that it's covariant with respect to the group generated by the clock Hamiltonian. So what I mean by that is that these clock states are all connected to one another by this unitary generated by the clock Hamiltonian. And if this is true about these clock states defining the effect operator, then this time observable will estimate on average for you the correct time read by the clock, which you would expect. So that might be a bit abstract. I want to give two just concrete examples. The first is a really simple one, very analogous to a position measurement. Let's imagine our clock is just a particle moving along the real line, right? Just at a constant speed. Well, the Hilbert space is L2R. We can imagine the Hamiltonian to be just a momentum operator, right? It generates translations in position. And so all the clock states are going to be related by this unitary generated by the momentum operator, which is exactly like the position eigenstates. So these would be our clock states. We can form those effect operators. And in this case, we can actually define a self-adjoint time operator, namely the position operator, namely where this particle is, right? But you might say, well, okay, this wasn't a physical Hamiltonian. It's not bounded from below. And I know something about Pauli's argument, so maybe I can't always do that construction. But this is where that more general notion of a positive operator value measure as an observable comes in. Because we could instead consider as a clock just a spin 1/2 particle processing around the z-axis, because it's in a magnetic field or something like that. So its Hamiltonian is just proportional to sigma z. And then our clock is basically, if we just think of moving a point around the equator of the Bloch sphere, right? So those would be our clock states. And then we can define effect operators with these clock states. And again, they define a proper quantum observable. But in this case, because these clock states aren't orthogonal, right, then we don't get a self-adjoint operator. But again, we still have a notion of a clock and a time observable for the spinning. So that's the big idea, is we have these clock states and we can use them to define time observables for different systems depending on their particular Hamilton. Okay, so that was the first part. I now want to tell you a little bit about this relational quantum dynamics. And the big idea there is we have some system of interest, and we're interested in describing its dynamics relative to another system that's working as a clock. And the way we're going to do this is we're going to have one big state, I'm going to call a physical state, this capital psi, that describes both the system and the clock. And it's defined such that it's in the kernel of a particular constraint operator. So I'll motivate exactly why you might want to consider this. But the idea here is that we're not going to postulate a priori the Schrodinger equation or unitary evolution. Rather, just by asking conditional questions about what the system is doing when the clock is reading a particular value, we'll recover as a consequence the Schrodinger equation in unitary dynamics. So why might you want to look at this formulation of dynamics in the first place? And really the motivation here is from quantum gravity, even though I'm going to use it later in the talk to talk about just relativistic quantum mechanics. If we think of most of our formulations of physical theories, we talk about matter evolving on some background space-time, right? Maybe in quantum field theory, for example, we impose equal time canonical commutation relations. So this background space-time structure is used as a construct in building our physical theories. However, in general relativity and presumably quantum gravity, the situation is very different, right? Is space-time is now a dynamical entity that interacts with matter. So it's not like it's this fixed absolute entity that we can use in building our quantum theory, but rather we have to quantize matter and space-time geometry sort of simultaneously. And so one way you might go about doing this is the following. So a very conservative approach to quantum gravity might be, let's just take general relativity and write it in a Hamiltonian form, right? And in this case, we're going to need a configuration variable that would play the role of a position coordinate. And for gravity, the configuration variable is the 3 metric describing spatial geometry. Yeah, and this is the thing that evolves, and when we glue a bunch of 3 geometries together, we get a 4-dimensional space-time. This is a picture from a nice essay John Wheeler wrote, showing a path in this, what he calls superspace, which is the configuration space of this geometry here, this 3 geometry. But anyway, so we have a configuration variable, we have a 3 metric, it has a conjugate momentum, and then we just take standard general relativity and we write it in a Hamiltonian form. And we get something that looks like this. So here we have a term that's quadratic in the momentum. So that's like a kinetic term. We have a potential that depends on the metric. And then if we have some matter degrees of freedom, the stress energy tensor appears there, and it's coupled to the gravitational degrees of freedom this way. So that's the Hamiltonian of the theory. But it turns out that it's constrained to vanish. It has to equal 0. That's a constraint of the theory. So that's a bit odd, but let's see how that plays out in the quantum theory. So how might we go about quantizing this theory? Well, one way is this so-called Dirac prescription or canonical approach that says when you have a classical constraint, something like this, right? Well, what you do is you promote it to an operator. So we put hats on our momenta and our configuration variable, and we demand that the physical states of our theory, these capital psi that are going to describe our 3 geometry and our matter, are annihilated by this constraint. So that's the first step. And then the second step is you want to impose some dynamics, right? So you maybe you want to postulate the Schrodinger equation, right? And if you wanted to do that, you'd say, well, this state evolves in T, well, that evolution is generated by the Hamiltonian. But then because of this constraint, we find that the state of geometry and matter doesn't evolve. It's actually frozen, right? So this is a bit of a problem then, in the sense that, you know, we see evolution and dynamics all around us, yet our theory isn't, we're not seeing any dynamics here. But if you think about it for a little bit more, you think, well, the main lesson of general relativity is that there isn't a preferred time direction or time coordinate. And so it would be weird if the Hamiltonian of GR selected a particular one. So it kind of had to be this way. And the idea is that instead dynamics is now going to emerge from a relational picture internal between, you know, these gravitational degrees of freedom and the matter energy. So I don't want to do quantum gravity today, so let's just look at a simpler system, but it's going to have the same logic and setup. We're going to have a constraint here, and we're going to demand that the physical states of our theory are annihilated by this constraint, just like on the previous slide. except our constraint's going to be a lot simpler. It's just going to be the sum of the clock Hamiltonian and the system Hamiltonian. So again, here's our clock and here's our system, and our constraint is just the sum of their Hamiltonians. So you can think maybe this has to be an energy eigenstate or something like that for this total Hamiltonian. Well, I can introduce this time observable that I spoke about at the first part of the talk, right? These are covariant clock states that are covariant with respect to this clock Hamiltonian. And then maybe I'm interested in some system observable, maybe the spin along a particular direction with outcome A, okay? And then this approach to relational dynamics was put forth by Don Page and Bill Wooters, and the main conceptual step here is to say that dynamics is really about conditional probabilities between the system and the clock. Namely, what is dynamics? It's saying something about the probability of A, of getting outcome A, when the clock reads outcome T. Yeah. And so what you can do is you can compute this conditional probability just using, again, the standard Born rule and formula for conditional probability, given the system is in this physical state here, annihilated by the constraint. So here's the probability of outcome A and the clock reading the time T, divided by the probability of the clock reading the time T. And it turns out that this conditional probability, if you define this conditional state of the system by taking this joint state of the clock and system and conditioning it on the clock reading the time T, then this is what hooked me. This is what was amazing, is that this conditional probability looks exactly like the usual probability amplitude squared of standard orthodox quantum mechanics. And moreover, this conditional state satisfies the usual Schrodinger equation. So what I find amazing about this construction is that just starting from a state and correlations in that state, and then asking kinematical questions, right? Not about dynamics, but about probabilities of outcomes, one recovers dynamics. It becomes derived just from sort of correlations and measurement structure of quantum. Okay. All right, so those are the two topics. I now want to apply those to this quantum time dilation effect I mentioned in the outline. And the setup is this, that I have two clocks here. They're going to have a covariant time observable associated with them. And one moves in a superposition of two different momentum wave patterns. What is the time dilation of clock A relative to clock B? And how would I go about answering that question? And the first thing to realize is that these are quantum clocks, so I'm not going to have a deterministic relationship between the time dilation read by these clocks. And so really what I should be looking at is conditional probabilities, just like the ones I introduced on the previous slides here. So what we're going to look at is constructing a probability distribution that the clock reads this one reads a particular proper time tau A, when clock B reads a particular time tau B. And then we'll look at the average of this probability distribution. So the model that we used was, we considered just a relativistic particle moving through space-time. So it's described by an action that looks something like this. So here's the usual contribution for just a free particle with mass m. And then we suppose that the particle was carrying some internal degrees of freedom that evolved according to the proper time of the particle. So that looks something like this. And these internal degrees, this would be the Lagrangian, these internal degrees of freedom, because they evolve in the proper time of the particle, we're going to use them as a clock to track the proper time of that particle. And namely, we're going to, this is the Hamiltonian of the clock, and we're going to define covariant time observables relative to this clock Hamiltonian. So you can carry out the Hamiltonian analysis. You again get a constraint. This is, you probably recognize as the relativistic dispersion relation, except now here, this m is not this non-dynamical mass m, but really it's promoted to this mass operator here, where we still have the little non-dynamical m, but it also receives a contribution from the internal energy of the clock. This is a quadratic equation in P, so we can factor it into two terms. And basically, if either one of these two factors is zero, then the constraint is going to be zero. And what that amounts to is basically, if we impose one or the other, we either restrict to positive energy solutions or negative energy solutions. So either matter or antimatter. So we'll restrict to just matter solutions. So the C plus. and then we'll build the quantum theory of that relativistic matter. So here we're going to say that our physical states describing the external spatial momenta and temporal coordinates of the particle and its internal mass operator, the physical states are annihilated by this constraint here. Okay. So with that as the setup, we can now put a little bit more detail. We'll consider this clock A to be moving in a superposition of Gaussian wave packets localized with average momenta p bar and p bar prime. And then we'll put them in an arbitrary superposition weighted by cosine theta and sine theta and have a relative phase phi between them. And then we can go and calculate this conditional probability distribution. What's the probability clock A reads the time tau A when clock B reads the time tau B? So again, it looks something just like this, the probability of tau A and tau B normalized by the probability of tau B. And then what you can do is compute the average of this probability distribution. And what you find is the average value of tau A is related to the time being conditioned on tau B by this multiplicative factor out front here. So here's the average time read by clock A. What you see is it's a sum of two contributions. The first is what we call this classical time dilation. This is just a statistical mixture of the time dilation you would expect of just a regular classical clock moving along either one of these definite trajectories. But then there's this quantum contribution that now depends on the relative phase between these wave packets and their separation in momentum space. So this gamma Q inverse is what's interesting. I want to show a plot of it here. So here I'm plotting for different sums of the average momenta of those wave packets. I'm plotting as a function of the difference, the magnitude of this gamma Q. So there's a few things you see is when those wave packets overlap exactly, this gamma Q vanishes. And then when they're infinitely far apart, it also vanishes. And then for a given sum of their average momenta, there's an optimal separation in momentum space to maximize this gamma Q. But now the question is, can we see this in a potential experiment? So we did some follow-up work with the group in Warsaw, where we did an honest quantum optics calculation. So we considered, let's suppose we have a two-level atom, okay, and we're going to consider as the clock the spontaneous emission from this excited atom. And we'll consider its center of mass to be put in a superposition, just like I described on the previous slide. And so we can use standard Hamiltonians that can be found. There's this nice recent paper as well that came out deriving these as well, where for our atom, well, we have our center of mass contribution with the first relativistic correction. So this is the non-relativistic kinetic energy. We have the internal energy here. And then because of the relativistic motion, we get this coupling between the internal and external center of mass degrees of freedom. That's going to all be responsible for the clock time dilating. And then we have a field, the electromagnetic field Hamiltonian, and then we have a coupling between the atom and the field, namely this dipole interaction and this correction from the Rankine term here. And then what you can do is consider, look at spontaneous emission rates and how it depends on the coherence in the center of mass wave packets. And if you compare a superposition versus a classical mixture of these wave packets, you find that the difference is exactly that gamma Q inverse that I derived on the previous slides. So suggesting that for this, different clock that we're looking at here, just a spontaneous emission, it also experiences the same interference effect. The other thing that I think is a bit harder to measure is you actually get corrections to the emission spectrum on account of the coherence in these wave packets. So here, what I'm plotting is the emission spectrum perpendicular to the motion of the atom. And what you see is you get two different peaks here of emitted radiation corresponding to the Doppler shifts associated with the momentum. But then when compared to a superposition in red versus this classical mixture, you actually see the shape depends on this coherence between these wave packets. The question is this observable? I realize I'm cutting close on time and I'm the last talk of the session. So the point of this slide here is that if we take sort of state-of-the-art numbers from what we've measured relativistic time dilation at and how large of these momentum superpositions we've created, this gamma Q is on the order of 10 to the minus 15. And so long as we can keep the coherence time of these superpositions, say, on the order of a second, then this would be within the resolution of current state-of-the-art atomic clocks. One thing I want to share is maybe a potential setup. I know there's a lot more accomplished laser physicists in the audience than myself, but this is one schematic that we've been thinking about. Here's a standard atomic clock setup where maybe we have some rubidium atoms, they're coming in, and we select just the ones in the ground state, and they have some momentum. And then what we try and do is we try and excite them with some radio wave source, and then we see how successful we were here in exciting them, and then we adjust our oscillator and tune this, and then we get a really accurate frequency source based on this energy gap here. But what happens if we put in a momentum beam splitter here, such that after the momentum beam splitter, the internal degree of freedom is still in its ground state and factored out from the center of mass degrees of freedom, which are now in a superposition of two different momenta? Then the radio wave source that's going to be most resonant with this superimposed atom is going to depend on this coherence between these two wave packets. And so maybe by imagining a setup like this and tuning the radio wave source, we'll be able to see evidence of this gamma Q. So with that, I want to end there. I gave you a quantum description of clocks, really motivated from a quantum metrology perspective in terms of these covariant time observables. I spoke to you about relational quantum dynamics, motivated from quantum gravity and the Page-Wouters formalism, and then I concluded with this quantum time dilation effect. So with that, I'll end there. Thank you.
Thank you very much, Alexander, for presenting us clear concepts on how time is to be viewed in the quantum world. There have been some controversies.
Yes.
Are there questions? So let me ask.
See one question from. Oh, sorry.
Oh, yes, Vitaly.
May I ask you just a general question? In your definition of the relational clock, which is a system that measures the time for the another system, it was stated, formulated in a kind of global, non-local sense. If the measured system is non-local, like the macroscopically extended system or the whole universe, then the question is at which point in space the clock measures the time. It somehow measures the time for the whole system, not just for local position. Can you clarify what?
Yeah. So, I mean, in the context of quantum gravity, that's quite interesting, because here the space-time in the metric, which is describing all of space, is being treated as a quantum degree of freedom. So to say something meaningful there, that's maybe a bit above my pay grade, I could speculate, but in the context that I was talking about, the clock had its own positional degree of freedom that could be localized sort of within sort of a standard quantum mechanical setting. But
it measures the time for the system, which is a finite size system. At which point of the system, or it is assumed that the time is the same over the whole system, say the whole universe or whatever.
Yeah, okay, maybe I would say it like that, is that it's defining a time t, a parameter t, that I can correlate with other things going on.
Non-locally.
Meaning those other things don't have to be located where the clock is. I'm not sure if that's getting at your question.
It's my question. I still don't understand how you can assign the time globally to the other system, which is non-local. The time at which point of other system? It looks like a time of the clock itself, but not the time which we can use to specify the time at different positions over the system we are measuring.
I would say like time is always a property of the clock. It's always an observable we measure on the clock. So like even in the laboratory, I look at my clock on the wall. It has nothing to do with, you know, me sliding a ball down a ramp or something like that. So,
Yes, I see. Okay, thank you.
yeah, no, thanks for the question.
Okay, well, in view of the fact that it's quite late already, we are now going, at least in Germany, going to go to bed with all these nice ideas from the different talks of today. So thank you very much to all speakers, and we will reconvene tomorrow.
And thank you so much, Jose. And I hope to see everybody tomorrow morning. Good night.
Good night.
Thank you.
Good night.
Good night.